All right, I'm pre-recording class for class E because I have a doctor's appointment during class on Monday. So I'll still be there the first half of class, but the second half of class, I have an appointment that starts at 2 o'clock. So I'm gonna have to leave before that. So here is the information I would be presenting on Monday, but won't get through all of it. So I'm gonna remind you all of some of the identities we talked about last time, specifically the quotient identities. The most important ones, tangent to theta equals sine theta over cosine theta. Cotangent to theta equals cosine theta over sine theta. Secant of theta equals 1 over cosine theta. And cosecant of theta equals 1 over sine theta. Those are the ones we use the most often. There's also tangent of theta equals 1 over cotangent of theta. They're reciprocals. Cotangent theta equals 1 over tangent theta. They're still reciprocals. Sine of theta is also equal to 1 over cosecant theta, just like cosecant theta is 1 over sine theta. They're reciprocals. And cosine of theta is the reciprocal of secant. So cosine theta equals 1 over secant theta. So if things are reciprocals, one of them is always equal to 1 over the other one. And it doesn't matter if it's this way or this way. It just depends on what's most useful to you. Then we also have the Pythagorean identities. The most famous one, sine squared theta plus cosine squared theta equals 1. Sometimes we rewrite this as sine squared theta equals 1 minus cosine squared theta. Or sometimes it's more useful as cosine squared theta equals 1 minus sine squared theta. Similarly, we have I tan and get sexy. 1 plus tangent squared theta equals secant squared theta. And sometimes it is useful to rewrite this as tangent squared theta equals secant squared theta minus 1. We almost never rewrite it any other way. In a similar vein, we have 1 plus cotangent squared theta equals cosecant squared theta, or sometimes it is useful to write cotangent squared theta equals cosecant squared theta minus 1. So now all we're going to do today really is do more examples of simplifying trigonometric expressions using trig identities to get down to usually a simpler thing. I might think most of my examples, we get down to one term, but always we're trying to kind of make the expression as simple as possible. So let's look at a few examples. Let's look at, say, some of the paper straight here. Let's look at 1 minus cosine of beta times cosecant of beta plus cotangent of beta. And you have a couple options here. You could FOIL this out first. I don't think that's what I want to do. I don't know, maybe, no, I don't really want to. Instead, I'm going to note that cosecant and cotangent have different forms. I'm going to write this as 1 minus cosine of beta times cosecant of beta, which is 1 over sine of beta, plus cotangent of beta, which is cosine beta over sine of beta. And noticeably, they have the same denominator. So I can totally make that 1 minus cosine beta times the fraction 1 plus cosine beta all over sine beta. And if I really wanted to, I could write this as 1 minus cosine beta over 1. Let me grab my red pen. Right, you don't have to. When you're multiplying something times a fraction, you always multiply the something that's not in a fraction by the top part. So I'm going to have 1 minus cosine beta times 1 plus cosine beta all over 1 times sine beta. So I'm not going to multiply it out just yet because I just want to show it. It's 1 minus cosine of beta times 1 plus cosine of beta all over sine of beta. If you're more comfortable, you might want to put your angle in parentheses. It's not really necessary, but you might feel better about it. And now we are going to FOIL. 1 times 1 is 1. 1 times cosine beta is plus cosine beta. Negative cosine beta times 1 is minus cosine beta. And negative cosine beta times cosine beta is minus cosine squared beta all over sine of beta. I was going to say, oh, you could like draw the little thing, like we FOIL that, right? This times this, this times this, this times this, this times that. Whatever you like. The middle terms cancel. That's what happens when you multiply conjugates together. 1 minus cosine beta and 1 plus cosine beta are conjugates. And so we end up getting 1 minus cosine squared of beta over sine of beta. And then 1 minus cosine squared beta is the same as sine squared beta. Sometimes people leave out the of, right? It's sine of beta, but sometimes we just say sine beta. And then one of those cancel. So it's just equal to sine of beta. And that's it. That's as simple as it gets. Let's do another one. This one's a little trickier. This next one is starting with sine of alpha over secant of alpha minus cosine of alpha. And again, we're kind of at a place where it's like, I don't know what to do. So what I'm going to do is I'm going to typically anything that isn't sine or cosine, so tangent, cotangent, secant, or cosecant, one of kind of the main tricks or plans of attack is to rewrite everything in terms of sine and cosine. So I'm going to rewrite this as sine of alpha divided by secant is 1 over cosine of alpha minus cosine of alpha. And now you have a choice. You could either multiply this by cosine over cosine to get a common denominator, or you could multiply the whole thing by cosine over cosine. I think the kind of more, it's easier to do the second thing I said, but it's more straightforward to do the first thing. So let's multiply the whole thing by, sorry, not the whole thing. Let's multiply this cosine down here, this cosine over 1 by cosine of alpha over cosine of alpha. So I'm going to get sine of alpha still on top over 1 over cosine of alpha minus cosine squared of alpha over cosine. Which I can then put that in, I can put those two fractions together and get sine of alpha over 1 minus cosine squared of alpha over cosine of alpha. At this point, you could either change 1 minus cosine squared to sine squared, or copy dot flip, right, where you flip and multiply by the reciprocal of the denominator. Let's do it the second thing. It doesn't really matter which word we're doing. So I'm going to write this as sine of alpha times cosine of alpha over 1 minus cosine squared of alpha. And again, I remind you that sine of alpha is really a sine of alpha over 1. So I could totally write this as sine of alpha times cosine of alpha divided by 1 times anything is just the whatever, the anything. So I just have a 1 minus cosine squared, but 1 minus cosine squared, that's equal to sine squared of alpha. So I really have sine of alpha times cosine alpha over sine squared of alpha. And again, I can cancel a sine of alpha and a sine of alpha. I'm left with cosine of alpha over sine of alpha, which is cotangent of alpha. I'm sorry. And then just to kind of point out, from this step here, we could have done a different thing. We could have instead said we have sine of alpha over 1 over cosine of alpha minus cosine of alpha, and just multiplied the entire top and the entire bottom by cosine of alpha. So then the top is just sine times cosine, so sine of alpha times cosine of alpha. The denominator, we have to distribute the cosine of alpha. Cosine of alpha times 1 over cosine of alpha is just 1. And cosine of alpha times negative cosine alpha is negative cosine squared alpha. And look, we're exactly back to where we were right here. We have sine times cosine over 1 minus cosine squared. Sine times cosine over 1 minus cosine squared. That's going to end up being the same as this. So we're going to end up getting cotangent of alpha again, which we should, right? No matter how we do it, if we simplify it as much as possible, we should pretty much get to the same place no matter which route we take. All roads lead to somewhere, the same place. Let's look at another. I want to change this one up. No, this one's good. I feel like, so a lot of these end up having the same trig identity. That's kind of the way things go. So let's look at sine of theta minus 1 all over sine of theta times 1 plus cosecant theta. So one way to go would be to write everything in terms of sines and cosines. You could write this as, well, in fact, yeah, I'm kind of, it always kind of depends. I'm going to go actually a different way. So I'm going to do this as, I'm actually going to divide each thing here by the sine. So I'm going to have sine theta over sine theta minus 1 over sine theta times 1 plus cosecant theta. And then sine over sine is 1. And 1 over sine is cosecant theta. So you have 1 minus cosecant theta times 1 plus cosecant theta. And we know that when you have conjugates multiplied together, right? A thing minus a thing, and then the same thing, but plus the other thing. Those are conjugates. And when you multiply conjugates together, the middle terms cancel. So we're just going to get 1 times 1, which is 1, minus cosecant squared theta. Right? The 1 times 1 is from there. And the minus cosecant times cosecant is there. And then the minus cosecant times 1 and the positive 1 times cosecant, that would give you a negative cosecant plus cosecant, which would cancel out. So we don't write them down. And then negative 1 minus cosecant squared theta is equal to, what is it equal to? I don't remember exactly. I know that 1 plus cotangent squared theta equals cosecant squared theta. So I guess I could substitute that in for cosecant squared and get 1 minus 1 plus cotangent squared theta, which is going to be 1 minus 1 minus cotangent squared theta, right? Distributing the minus sign. And then the 1 minus 1 cancels, and we get negative cotangent squared theta. And that's probably, I don't know, maybe the most straightforward way of doing it. Maybe not. There could be other straightforward ways of doing it. But that's kind of the way I am seeing it. Yeah. Yeah. And you could do something else like, so just as a counterpoint, instead, you could do this as sine theta minus 1 over sine theta. And you could rewrite the 1 plus cosecant theta as 1 plus 1 over sine theta. And then you could get a common denominator here, right? This is going to be sine over sine. So that's going to be sine theta minus 1 over sine theta. And then sine over sine plus 1 is going to be, sorry, sine over sine plus 1 over sine is going to be sine of theta plus 1 over sine theta, right? Because that right there is really sine theta over sine theta. So then we can multiply, when you multiply fractions, you top times top, bottom times bottom. So that's going to be sine of theta minus 1 times sine of theta plus 1 all over sine squared theta. So I'm going to get sine squared theta and then minus sine theta plus sine theta. Those will cancel out just like they always do with conjugates. And then a minus 1 times 1 is minus 1. All right, so again, just to point out, the sine of theta times 1 would be a positive sine theta, and the negative 1 times sine theta would be a negative sine theta, and those would cancel out. Whereas the sine squared and the minus 1 are still there. And here's something to be careful about. We can't cancel the sine squareds there. Right? You can't cancel that until you get negative 1. That would be totally wrong. What you could do if you wanted to is you could say you've got sine squared theta divided by sine squared theta minus 1 divided by sine squared theta. And then sine squared over sine squared is 1, and 1 over sine squared is cosecant squared. And then we're back to right where we were here. And then we would do the same thing to get negative cotangent squared. Or you do something else and say, well, I know that sine squared theta equals 1 minus cosine squared theta. So then you can replace this with 1 minus cosine squared theta minus 1. And we're just replacing the top sine squared. We're leaving the bottom sine squared as is. And then the 1's cancel. You get negative cosine squared theta over sine squared theta But cosine over sine is cotangent, so cosine squared over sine squared is cotangent squared. So we do get negative cotangent squared theta. So what I'm really trying to show you here is that there's kind of a lot of different ways to go. And as long as you're doing the right things, you'll get to the right place. So let's look at the next one. Also, I should point out, if you look at module D, I did make some extra videos. They say like trig identity video 1, or something like that, and video 2. Those also have some good examples. And I think I might have made videos for these already, but I can do them again. I don't mind. So let's look at this one. Cosine of x over cosecant of x minus sine of x. Again, I'm going to go back to kind of my, oops, sorry, let me fix that. My default kind of, let me do this a little bit. That'll help. My default plan of attack is usually to write things in terms of sine and cosine. So I'm going to write this as cosine of x over 1 over sine of x minus sine of x. And then I'm going to get a common denominator. I'm going to take the sine of x over 1 and multiply it by sine of x over sine of x. So then I'm going to get on top cosine x. On the bottom, I get 1 over sine, and I have sine squared over sine. So I have 1 minus sine squared x over sine of x. Okay, now we can replace 1 minus sine squared with cosine squared. Or you could flip the multiply first, either way. You can say it's cosine of x times sine of x over 1 minus sine squared of x. But you really can't really when you have a fraction in the bottom, at some point you almost always have to kind of flip it over and multiply by it without kind of doing anything else. And then we could write this as cosine x over 1 times sine x over cosine squared x. If you're perfectly fine jumping from this straight to cosine x times sine x all over cosine squared x, that is also really perfectly fine. And then the cosine cancels here and here. We're left with sine of x over cosine of x, which is our good friend, tangent of x. Let's do a couple more, and then we will look at a couple different things. So here's another one. Here's a funky looking one that I hadn't really paid attention to. This one might be easier than I mean to, that's okay. So I've got cosine of theta times 1 plus tangent squared. And yeah, this one will be kind of easy. So one way this is easy is to say, I know that 1 plus tangent squared is secant squared because I tan and get. It's actually right, I know, it's terrible. So 1 plus tangent squared is secant squared. So you have cosine of theta times secant squared theta. But then secant squared is 1 over cosine squared. And then you can cancel, like, whoops, cosine of theta. You need that theta there. It's really not right if there isn't an angle there. Cosine here cancels with the cosine there, because that's cosine squared is really cosine theta times cosine theta. So 1 of them cancels out. And you're left with 1 over cosine theta, which is secant theta. Well, let's pretend maybe we didn't see that 1 plus tangent squared was secant squared, or we forgot. You could also rewrite tangent squared as 1 plus tangent squared is going to be sine squared theta over cosine squared theta. And then you could actually, common denominator, yeah, common denominator, or distribute, no, I think common denominator. So you get a common denominator, cosine theta times cosine squared theta over cosine squared theta plus sine squared theta over cosine squared theta. And then you add these together. You get cosine theta times cosine squared theta plus sine squared theta over cosine squared theta. When you're adding fractions, the denominators have to be the same. And when you add them, you get the same denominator and you just add the tops. But then cosine squared theta plus sine squared theta is just 1, right? It's our most famous trig identity. And now we're back to where we got to the other one, right? Cosine theta times 1 over cosine squared. That's going to be 1 over cosine, which is secant. Okay. All right, I got one more of these, and then we'll look at a couple other things. if I can move the page here. So here's a less maybe normal looking one. 1 minus tangent of alpha quantity squared plus 2 times sine of alpha times secant of alpha. And we want to simplify this down to one term if possible. So I'm going to multiply this out. This is 1 minus tangent alpha times 1 minus tangent alpha. Notice that since they're both minus, the middle terms aren't going to cancel out, right? It's not 1 minus tangent times 1 plus tangent. So we are going to have some middle terms. And then we have got this. Do I want to do anything with that? Yeah, I'm going to change secant alpha to 1 over cosine. Okay. So then 1 times 1 is 1. 1 times negative tangent is negative tangent. So that's 1 times 1 times negative tangent. And then negative tangent times 1 is going to give me another negative tangent. So I could just say I have negative 2 tangents, but I'll write it out this way first. And then finally, negative tangent times negative tangent is positive tangent squared of alpha. Sine over cosine is tangent. So look, the negative tangent and negative tangent cancels out with the positive 2 tangent. So this and these cancel each other out. And then we have 1 plus tangent squared alpha, and you know what that means. I tan and get secant. Secant squared, 1 plus tangent squared alpha equals secant squared alpha. And that's our final answer. Okay, so that's it as far as the using the trig identities we know to kind of simplify trigonometric expressions, but then we also might verify some trig identities. So let's verify that cosine squared theta equals 1 minus sine squared theta for the following angles. So first we'll do it for theta equal to 4 pi over 3. It might help to remember the reference angle and the quadrant. So the quadrant is definitely quadrant 3, right? Because pi over 3 is in quadrant 1, 2 pi over 3 is in quadrant 2, 3 pi over 3 isn't in any quadrant, it's pi, it's a quadrantal angle, but 4 pi over 3 is in quadrant 3. And then the reference angle is, of course, pi over 3. So pi over 3, I didn't draw it very well, but we know that pi over 3 is the middle-sized angle, right? It's 60 degrees. The hypotenuse is 2. The smallest angle is 30 degrees, or pi over 6, and its opposite side is 1. And the middle side has an opposite side, has a value of root 3. So let's see. Here's how I like to work this. The left-hand side is equal to cosine squared of 4 pi over 3. We know we're in quadrant 3, so both sine and cosine will be negative. Cosine of pi over 3 is 1 over 2. So cosine of 4 pi over 3, sorry, one sec, let me write this. So I'm just going to remind you that cosine squared of 4 pi over 3 means cosine of 4 pi over 3 quantity squared. So cosine of 4 pi over 3 is going to be negative 1/2 quantity squared, which will be positive 1/4. And then to the right-hand side, as you use a colon here, not an equal sign, the right-hand side, 1 minus sine squared of 4 pi over 3 is going to be 1 minus, let's see, sine of 4 pi, let's actually write it out. It's sine of 4 pi over 3 quantity squared. And sine of pi over 3 is root 3 over 2. So sine of 4 pi over 3 is negative root 3 over 2. So we're going to get 1 minus, let's see, a negative number squared is always positive, so it's going to be positive, even though we're minusing it, we're minusing a positive number. Square root of 3 squared is 3, and 2 squared is 4. And 1 minus 3/4 is 1/4. And look, they're the same. That's what we wanted. We wanted cosine squared theta to equal minus sine squared theta. Let's do another one. Let's do the same, actually, identity for theta equal to 5 pi over 6. And let's use a different color just so it's easier to see what's happening here. So let's see, for theta equal to 5 pi over 6. So the reference angle here is pi over 6, which actually is this angle of this special triangle. and the quadrant is quadrant 2. So let's see, we're going to have the left-hand side. It's going to be cosine squared of 5 pi over 6. Cosine of pi over 6 is the adjacent over the hypotenuse, which is root 3 over 2. Cosine of 5 pi over 6 is in quadrant 2, so it's going to be negative. So it's going to be negative root 3 over 2, but then it's going to get squared. So it's going to turn out to be positive 3 over 4. The right-hand side is 1 minus sine squared of 5 pi over 6. It's going to be 1 minus sine of pi over 6 is 1/2. Sine of 5 pi over 6, since we're in quadrant 2, is also positive 1/2. So it's going to be 1 minus positive 1/2 squared. That's 1 minus 1/4. That's 3/4. Check. Great. Let's see what else we got left here. Not very much. So a couple more things. Another example. Let's do another one. Let's verify that 1 plus tangent squared theta equals secant squared theta for theta equal to 3 pi over 4. So the reference angle is pi over 4. The quadrant is 2. And in quadrant 2, sine is positive, which means tangent and cosine are negative, which also means secant is negative. It doesn't really matter, though, for these problems, whether it's positive or negative, because we're going to be squaring all of them anyway, so they all end up being positive. So reference angle is pi over 4 or 45 degrees. So here's our nice triangle, and it's a 1, 1, root 2 triangle. Or if you prefer, you could also do it as I've seen lots of things. You can do it as a root 2, 2 triangle. That also is totally legit. Okay, so let's see. Let's do the left-hand side. 1 plus tangent squared of 3 pi over 4. Let's see, tangent of pi over 4 would be root 2 over 2, or 1 over 1, which is 1. Tangent 1 squared is still 1, so you get 1 plus 1 squared, which is 2. The right-hand side, secant squared of 3 pi over 4. Well, secant, well, I never know what secant is. I always do the reciprocal of cosine. Cosine of pi over 4 would be 1 over root 2. So cosine of 3 pi over 4 would be negative 1 over root 2. So secant of 3 pi over 4 would be negative root 2 over 1, or negative root 2. So then secant squared of 3 pi over 4 would be secant of 3 pi over 4 squared, which would be negative root 2 over 1, but I'm not going to write the over 1 squared. And the square root of 2 squared is 2. So we get negative times negative is positive 2. Check, they're the same. Note, this identity is not true for an angle like theta equal to pi over 2, because for pi over 2, both tangent of pi over 2 and secant of pi over 2 are undefined. So a trig identity is only true as long as each trig function is identified at the angle that you're saying it's true at. So 1 plus tangent squared equal to secant squared is generally always true, except for angles where tangent or secant are undefined, like pi over 2, or 3 pi over 2, or 5 pi over 2, or any odd multiple of pi over 2. Okay, this last one we're going to do is kind of leading up to something which is going to be part of class F, but it seemed like a good place to put it. So we're going to verify the following statement. We're going to verify that sine of pi over 6 plus pi over 3 is equal to sine of pi over 6 times cosine of pi over 3 plus cosine of pi over 6 times sine of pi over 3. Let's do the left-hand side. Left-hand side's easier. So let's just add pi over 6 and pi over 3. So that's going to be sine of pi over 6 plus pi over 3, which is sine of, well, let's see, pi over 6 and pi over 3, I can multiply by 2 over 2 to get 2 pi over 6, which is going to be sine of pi over 6 plus 2 pi over 6 is 3 pi over 6. And that reduces to pi over 2. And we know that pi over 2 is a quadrantal angle. It's this angle at the quote unquote top of the circle. And the coordinate there is 0, 1. And sine is always the y coordinate. So sine of pi over 2 is 1. Great, let's check out the right-hand side. So the right-hand side, I'm going to use some triangles again. Here's my 30, 60, 90 triangle, or my pi over 6, pi over 3, pi over 2, right triangle. The hypotenuse is 2, the small side is 1. The small side is always the side opposite the smallest angle. And the medium side is root 3. So let's see. Sine of pi over, I'm going to write it out again. Sine of pi over 6, cosine of pi over 3, cosine of pi over 6, sine of pi over 3. So sine of pi over 6 is opposite of hypotenuse, so that's going to be 1/2. Cosine of pi over 3 is adjacent of hypotenuse, which is also 1/2. Cosine of pi over 6 is adjacent of hypotenuse, which is root 3 over 2. And sine of pi over 3 is opposite of hypotenuse, which is also root 3 over 2. 1/2 times 1/2 is 1 times 1 over 2 times 2. Root 3 over 2 times root 3 over 2 is root 3 times root 3 over 2 times 2. And 1/4 plus 3/4 equals 1. Check. So what this is leading us towards, or kind of alluding to, is what's known as the angle sum formula, which is sine of A plus B, where A and B are both angles, is equal to sine of A times cosine of B plus cosine of A times sine of B. But we will talk about that more in class F. So thank you for watching the video. I'm sorry I couldn't be here for class all the full hour that I usually would be, but it was very hard to get this doctor appointment and I need to keep it. So it's nothing too major, just I need to see the doctor. I'll see you guys tomorrow.